So far we've looked at scaling objects and at units. Now we're going to look more at some real-world applications of these ideas. Is it possible to scale any object up to any size that we can think of? It turns out that there are physical limits on how big things can be, and one thing that limits how large an object can be is gravity. When we're measuring the weight of an object with a scale, what we're actually measuring is the amount of force on that object due to gravity. And in fact, weight is going to differ depending on where you measure it, depending on the elevation. So the standard weight is going to be the weight measured at sea level. There are some new ideas in this section, and the first important one is density. The density of a material is its weight per unit volume. So density is equal to weight divided by volume. Another useful way to write this equation is if I multiply both sides by volume, that will tell me that weight is equal to density times volume, and that might be useful in some problems where you're given the density and the volume but not the weight. To find the density of a material, we can measure the weight in pounds of a cube made out of that material with 1 foot sides. So what does that mean? So if I've got a cube made out of some material with 1 foot sides, so this is 1 foot, then the volume of that cube is going to be 1 cubic foot, and the density is equal to weight divided by volume, so that's going to be weight divided by 1 foot cubed, or weight times 1 over 1 cubic foot. So that's useful. So if I look at this chart here, it's got some densities of common materials, and you can figure these out by weighing a cube with 1 foot sides. So if you weigh an aluminum cube with 1 foot sides, that's going to weigh 171 pounds. So that means its density is 171 pounds per cubic foot. And then I've also got the densities for water, dry sand, compacted snow, and steel here. Another big idea in this section is pressure. Pressure is the amount of force exerted per unit area. In our case, the force that we're interested in is the weight of the object on the bottom face of the object. So we can think of pressure as the weight per unit area of the bottom face of the object, or pressure equals weight divided by area. So let's look at a short example of that. Suppose we have a 1 foot cube made out of steel. 1 cubic foot of steel weighs 500 pounds, and the area of the bottom of the cube is 1 foot by 1 foot, or 1 square foot. So then I can find the pressure by dividing the weight by the area, and that's going to be 500 pounds divided by 1 square foot. So the pressure on the bottom of that cube will be 500 pounds per square foot. So like area and volume, pressure is also going to scale with size. So let's look at how that works. Here I've got my 1 foot cube made out of steel, and the pressure on the bottom of that small cube that we just saw on the last slide is 500 pounds per square foot. Now I've scaled this cube up with a linear scaling factor of 3. So this larger cube has sides that are 3 feet long, and its volume is 27 cubic feet because volume scales like L cubed, or 3 cubed, which is equal to 27. the bottom surface area of this larger cube is going to be 9 square feet. It'll be 3 feet by 3 feet. And the weight scales like volume, so the weight of the large cube is going to be 500 pounds times L cubed, which is 27. So that's going to give me 13,500 pounds as the weight of the large cube. So continuing on, I can calculate the pressure on the bottom of the large cube. Again, pressure is weight divided by area, so I know the weight of the large cube is 13,500 pounds. And the area of the bottom of the large cube is 9 square feet. So if I divide that, that's going to give me 1,500 pounds per square foot as the pressure on the bottom of the big cube. And if we remember, for the small cube, I had a pressure of 500 pounds per square foot. So the pressure on the bottom of the large cube is 3 times the pressure on the bottom of the small cube. If you think about that for a while, that kind of makes sense because there is 3 times as much weight over each square foot of the large cube on the bottom because the cube is 3 times as tall. So just to summarize, we can remember how area and volume scale from section 18.1. Area is proportional to L squared, and volume is proportional to L cubed. We also know that weight scales like volume, so weight is proportional to L cubed. So now we can see that pressure is proportional to L by taking these things into consideration. So pressure is equal to weight divided by area. We know weight's proportional to L cubed, and area is proportional to L squared. So L cubed divided by L squared is just going to be L. So this tells me that pressure is proportional to L, which is what we saw in that example with the cube. So let's look at the example of an even bigger cube. Here I've got a 10-foot cube, so it's scaled up with a linear scaling factor of L equals 10. And I want to find what the pressure on the bottom of this steel cube is. So I know that the small cube has a pressure of 500 pounds per square foot. And I know that pressure scales proportionally to L. So that tells me that the pressure of the big cube is going to be L times the pressure of the small cube. So 10 times 500 pounds per square foot, which is equal to 5,000 pounds per square foot. So we've made a big cube and we've figured out what the pressure on the bottom is. But there's going to be some limit to this. There's going to be some point at which the cube is so big that it will start to deform under its own weight. The crushing strength of steel is about 7.5 million pounds per square foot of pressure. And crushing strength means that once we reach that amount of pressure, then the structure is going to start to deform under its own weight. It won't be able to support itself anymore. So since pressure scales like L, then the tallest steel cube that we can make will satisfy this equation. So I've got my maximum pressure over here is equal to the linear scaling factor times the pressure on my 1-foot cube. So if I divide both sides by 500 pounds per square foot, then that's going to give me a linear scaling factor of 15,000. So the tallest possible steel cube that you can make would be 15,000 feet tall, and that's just under 3 miles high. And we'll finish up by looking at a couple of more examples. The world's tallest skyscraper is Burj Khalifa at 2,684 feet. The building is made of reinforced concrete, which has a density of 160 pounds per cubic feet. And we want to find the pressure at the bottom of its walls. First of all, we're going to make some assumptions. The actual building tapers towards the top, but we're going to model it as just a rectangular solid, so just a tall rectangle like this. The volume of a wall is its height times the area of its base, so V equals H times A. And we're looking at the walls because the walls are what's supporting this structure. So the weight of a wall is going to be density times volume, and since volume is height times area, that's equal to density times height times area. Now to find the pressure, I know that pressure is equal to weight divided by area, and I know that weight equals density times height times area, so this is equal to dHA divided by A. Now my A's are going to cancel here. So the pressure on the bottom of the walls is just going to be the density times the height. I know the density is 160 pounds per cubic foot. And the height of this skyscraper is 2,684 feet. So what will that give me? Well, I've got feet here and feet cubed on the bottom here, so that's going to cancel part of this and give me feet squared now on the bottom. And if I multiply 160 times 2,684, that's going to give me 429,440, and I've got pounds per square foot for my pressure. So that is quite a lot of pressure. That's almost 500,000 pounds per square foot. We can look at the limit of how tall a building made of reinforced concrete can be. First, we need to know that the crushing strength of reinforced concrete is about 8.5 million pounds per square foot. We saw in the example that the pressure is going to be equal to density times the height of the building. So the tallest building that can be built will satisfy this equation. The density of reinforced concrete is 160 pounds per cubic foot times height is going to be equal to the maximum pressure or crushing strength, which is 8.5 million pounds per square foot. So I'm going to divide both sides by my 160 pounds per cubic foot over here. So that will tell me what H is equal to. Now I've got some interesting units here. So my pounds can cancel on the top and the bottom. And that's going to leave me with 1 foot squared over 1 foot cubed. When we divide fractions, it's actually the same as multiplying by the bottom fraction flipped over, so that's going to be equal to 1 foot squared times foot cubed over 1. And I'm going to have left is just feet on top, so that's equal to feet. And then 8.5 million divided by 160 is going to give me 53,125 feet. So since 1 mile is 5,280 feet, this is just over 10 miles tall. So that's a pretty high estimate actually for the height of the tallest building, because the walls not only have to support themselves, but they also have to support everything else in the building, including floors and any furniture or other things that are in there. Lastly, we're going to look at how high a mountain can be. How tall can a mountain be if we model it as a cone made of granite? And I'm given here that the density of granite is 165 pounds per cubic foot, and the crushing strength of granite is 4 million pounds per square foot. So first we're going to make some assumptions. We're going to assume that our mountain is going to be modeled like this, so it's a cone, and we're going to assume that the diameter of the base of the cone, or the distance across the base of the cone, is equal to its height. So in my little diagram here, that would mean that 2 times r is equal to h. And then some equations that we're going to need is the volume of the cone is given by this formula here, 1/12 pi times h cubed, where h is the height. And the area of the base of this cone is given by 1/4 pi times height squared. We know that weight is equal to density times volume. So to get the pressure, we're going to take the weight divided by area, or density times volume divided by area. And I've been given my density, and I've got formulas for volume and area, so we're going to use this formula and just substitute in our equations for volume and area. So that's going to give me P is equal to my density, 165 pounds per square foot, times the volume, which is 1/12 pi times h cubed, divided by the area is 1/4 pi times h squared. Now if I look at h cubed over h squared, that's equal to h times h times h over h times h. So 2 of my h's on the top are going to cancel with the 2 h's on the bottom, and that's just equal to h. And I've got some more algebra to do here, so I've got my numbers are 165 times 1/12 divided by 1/4, and that's actually equal to 165 divided by 3. So I'll box that off. So I can use that now to simplify my formula for pressure. I also notice that I've got pi on the bottom and pi on the top, so I can cancel those. What does that leave me with? Well, I've got all these numbers, 165 times 1/12 divided by 1/4, which I said was 165 divided by 3. And then I've got h cubed divided by h squared, which is h. And I've also got these units. I've got pounds per foot squared, so that's my simplified formula for the pressure on the base of this mountain. And now I wanted to know how tall a mountain could possibly be. So I know that the pressure on the base of the mountain with height h is given by this formula, and the crushing strength is 4 million pounds per foot squared, so that's the maximum pressure. So to find the maximum height, I'm going to set P equal to my maximum pressure, so 4 million, I'm just going to write that out, 4 million pounds per foot squared is going to be equal to 165 divided by 3 times h pounds per foot squared. And if I divide by 165 over 3, and I notice that I've got pounds per foot squared on both sides here, so I can just cancel those. So that's going to tell me h is equal to 4 million divided by 165 over 3. And if I put that in my calculator, that's going to give me 72 8,727 feet as the maximum height that my mountain can be. And the actual tallest mountain is Mount Everest, which is about 5.5 miles high, and this is about 13.8 miles high. So that's a lot taller than the actual tallest mountain, and there are probably some other limits besides gravity and crushing strength that mean that mountains can't be quite that tall. So that finishes up this section. Things that you should know. You should be able to understand density, pressure, and crushing strength. Calculate the pressure on the base of an object, and calculate the maximum size of an object.